Thanks. Thanks. So again, so I will talk about this work that a research intern student Aditya and a graduate student Maladeep. So Maladeep is sitting in the audience. So you must have seen him carrying mic around here and there for last couple of days. So that is why I did not put the picture here. So, okay. So what I will describe today is a very specific, let's say, very focused area. Right? So the conference is about fluid dynamics, and the work that I will describe has no dynamics. So it is a really static case. Velocity field is zero everywhere. And again, so all this discussion is relevant for when one wants to, one is interested in the numerical solution of multi-phase flow equations. So that is, let's say, that is the area for which I believe that this will be useful information. So let's say this photograph shows, okay, maybe it is not that clear, but you see that there are some red solid particles and there is some yellow color liquid you see, that is glycerol, and the black one is black phase is oil one. So what we have is really a three-phase system. Three-phase is one of them is solid and two of them are fluids. So one of them is solid and two of them are fluids. And what we are interested in is, let's say, if we impose some external flow, what is their rheological response, let's say. So we can impose various types of flow. One can imagine that depending on the strength of viscous forces or capillary forces, we will have different sorts of structures emerging from this. So this, the motivation for this work is because we have an experimental collaborator, Sachin Velankar, in Pittsburgh University. So who will be supporting us with experiments, and our job is to accurately model this, let's say, three-phase system. Usually I just say two-phase, but then two-phase sounds very simple, one solid and one fluid. But so that is why again three-phase, in the sense that one is solid and two are fluids. And again, the discussions are, whatever we say, are equally, let's say, relevant for wet granular flow. So what do you have to model this? If you want to, let's say, compare with experiments, what things one needs to model? Let's say we have, in this case, we have three phases. We say that there are one is solid, there are two are fluids. So this is the general situation we have. This, let's say, phi1, phi2, phi3 are phase fractions. So that indicates, let's say, the presence of that phase, solid or either of the fluid. Right? So one way to model this system is that we take an approach that we say that all of them have a slightly, let's say, they have a diffuse interface width, and at all the times, of course, independent of if it is a diffuse or not, we have to satisfy the constraint that the summation of the phase fraction has to be 1. Right? So this has to be, let's say, satisfied at every point, and not only that, we need to make sure that all the phase, let's say, if you are talking about immiscible fluids where there is no phase transition, then the mass fractions of these individual fluids also must be constant. Other type of, let's say, the other way to model the same system is that we say that there is only one, let's say, phase field or order parameter type of variable that will distinguish between two fluid phases, but the interface between solid and fluid are treated as sharp one. Again, in this case, we are only solving for, let's say, phase fractions 1 and 2. The phase fraction for solid, it is calculated, let's say, in a different scheme where we simply advect the solid. So given the velocity field around the solid, we can find the net force acting and the torque acting, and simply treat the solid as a rigid body and move that solid. Sorry, so I will just close one program that is. So in this case, we have only, the difference is that we have only one order parameter now. And natural question is, what is the difference between two type of approaches, and is one of them is preferred over the other? The answer is no, both of them suffer from the same difficulties. It is, to my knowledge, it is extremely difficult or more or less impossible to make sure that you satisfy mass conservation and momentum conservation exactly at the triple junction. So It is very difficult thing to achieve. There are some models, 3-phase models, but let's say in the diffuse interface framework, but they will work for a very limited range of Reynolds number. After that, they become unstable. So which one to prefer? You can do anything. So we prefer the second one because it is in line with the previous model we proposed in lattice-Boltzmann method. So what are the equations we are solving? We are looking for fluid motion, assuming that the fluids are incompressible, immiscible, momentum equation, and the difference, let's say, is that we define the curvature in terms of this order parameter, which is only takes care of the fluid-fluid interface, right? So it is not defined inside the solid. And then we have interface tracking, so which is very similar to again volume of fluid or other interface tracking schemes. In that other schemes, let's say, they essentially do the same thing. The aim is to advect this phase field or phase fraction information. In other methods, it is done in 2 steps. Here, it is done in the one single step. And the motion of rigid body is again, as we said, once we find out all the forces acting and the torque acting, we can simply translate the body. Next, this difference is now is very important. So the forces acting on the solid are of the 2 types. One is hydrodynamic forces, which result from the pressure and shear stress on the solid surface. The other ones are capillary forces. Right? So this is necessary because if you look at our previous formulation, right? So we are treating this interface between solid and fluid as a sharp one. So in fact, there is if we go from a solid phase to a fluid phase, we don't have any energy penalty or we don't have any order parameter defined that will take care of some energy penalty. In other words, so if you want to calculate the total force on the solid, we need to include this capillary force explicitly. Again, it is not a difficult thing to do. Once we find out what is the contact angle made by the fluid interface with the solid, we can write down the expression for force. To describe, let's say, this difficulty with capturing forces on solid correctly, we can start with a simpler case, which is the, let's say, most simple case that is possible. We will consider simply simulation of a pressure jump in a fluid drop, right? So the blue one is a fluid, the red one is fluid, there is no solid, and we expect that there will be a pressure jump. Pressure inside of this circle should be higher than the outside of very simple 2-dimensional geometry. So this part is important, that we will be working with only structured grid, rectangular grids, and also we will say that the grid spacing in either direction is same. So this is again the constraint we have because of the lattice-Boltzmann modeling. But again, although it looks like a constraint at the moment, it is also a nice feature. So this is the, let's say, we want to make sure that there is a pressure jump at the center and far away, or anyway, if you just cross this interface, we should see this pressure different. Again, a static situation. So if we simplify momentum balance, we have only pressure difference and surface tension force here. And if we write out, again, if you look at the interface evolution equation, we have 0 velocity everywhere. That means that the left hand side is 0, and we are looking at only at the right hand side. So that term is written. So that interface tracking term is written here. So what is important is that, let's say, these are the typical numbers. Let's say what we do is W is the interface width, and since it is a diffuse interface model, we need to make sure that W is at least somewhat more greater than the interface, the grid spacing. So in this case, let's say W is 4 times delta X. So you can see delta X is here. So W will be more or less occupying 4 points on either side of the interface. And since for this simple geometry, the radius is 6 times the interface width. So that will be 24. So for this very simple type of geometry, we expect that the pressure, of course, we should be able to calculate with whatever accuracy we want. But again, if you do the simulation, it doesn't matter what type of let's say solver we use. The pressure error in the pressure are of the order of 3 to 7%, right? which is still acceptable. So which is still acceptable because the system is consistent with itself. we don't have an unphysical motion of the drop. So the only meaning of this, let's say, error is that the pressure difference is, let's say, will be always slightly different than what we expect. Or in other words, the effective surface tension is different than what we want to set it here. So this is still perfectly fine, and one can expect that as we continue to increase the resolution of the system, resolution in the sense that both these numbers. So if we have a larger interface width and larger radius of the drop, then we should have better and better accuracy. Sorry, so I will just quit the program again. Yeah. So one expects that if we continue to increase the resolution, the error in pressure should be less and less. So this is what we expect. And again, as these are the two equations we have. Right? So this is okay for two-phase fluids. There is a slight problem once we introduce a solid now. So imagine that this is a solid plate on which we keep a drop now. And if we look at momentum balance for the drop, there will be net pressure force acting upwards in this direction, and the surface tension is trying to pull the drop down. And because of the again, in two dimensions, this surface can be, we can assume that it is a part of a circle, assuming that there is no gravity, right? So then the net force acting on the drop becomes zero. So this is exactly the equal and opposite force that should be acting on the solid. So the force acting on the solid is only changes sign. So the pressure is acting downwards on the solid, and the surface tension is trying to pull it upwards. So if we do this, we saw in the last slide, if you do this, we will find that there will be a net pressure force acting on the solid plate because the numerical scheme gives a pressure difference already at this, let's say, relatively coarse resolution. Right? So the pressure difference is different than what we are setting here. So in other words, now there will be a net force acting on this solid. This was okay for if we have only two fluid phases, but if you have solid now, we have a problem. So this force, as you can see, it will be simply proportional to the surface tension, and if you look at the order of magnitude of errors, then it will be always somewhere between 2% to 7%. Right? So although we don't expect any force on the solid plate, now we will have a motion of solid with a given constant force, and that will make all the difference if you want to do simulations of suspensions in two-phase flow. So the question is this: that what we can is there any way where we can, although there are this discretization errors, can we minimize them? That is the question. So again, what we want to keep in mind is that, let's say, this erroneous force is roughly, let's say, 5 to 7% of the total capillary force acting on the plate. So to look at this now, we simply look at what type of numerical stencil we are using to solve this interface tracking equation and momentum balance equation. So this is the, let's say, typical stencil that is used in lattice Boltzmann in two dimensions. So we show here, let's say, these 8 points, and if you include also the center, these are 9 points. That is why it is D2, Q9. And again, so this all these neighbors, 5, 3, 2, 6, all of these neighbors have a certain weight assigned to them, and if we simply compute the weighted average, we can write the derivatives at this center in terms of the values of these neighbor points. So if we do that by simple Taylor expansion, we can find that in fact the numerical derivative is gradient or Laplacian is in fact the analytical value that we expect, and the error terms that can be written in terms of, let's say, the grid spacing. So in both dimensions x and y, the grid spacing is same. So only delta x square appears. Otherwise, we could have also delta y square term. And the nice part of this lattice is that it is symmetric. So if any type of asymmetry will appear only after delta x to the power 5. So until delta x to the power 4, the operator is really isotropic, which also helps in our in the next steps. Similarly, we can also write down the Laplacian. So numerical Laplacian is slightly different than the what we want to impose there. And as we saw, if you look at the problem again, we have two dimensionless numbers. One is the resolution of the interface width, And the second part is how large is this interface width compared to the characteristic length of the problem. So in the characteristic length, in this case, is simply the circle, the radius of the circle. So this is the another parameter we are looking to incorporate in our let's say understanding. So to do that, what one can do is we can simply write the differential operators again in curvilinear system, so that we are now not restricted to a circular geometry, but it can be any arbitrary. So this is, let's say, the Cartesian coordinates x and y. The points, any points on the surface are given, we show with the letter P, and we can draw tangent and normal directions at this point. And since these are local coordinates, as we move along this any surface, we can this orthogonal coordinate system will be attached to that point, and we can move along the surface. So using simple geometry, we can convert our rectangular gradient operators in curvilinear one. So these are the expressions. Here kappa appears as a curvature. This is the divergence. This is the usual Laplacian. And since we are looking for, as we saw in the previous slide, that error terms goes as Laplacian square and divergence of the Laplacian here, we need to also write them down. So these are the, let's say, the complete expressions. An important thing to note is that we have only, let's say, in all these derivatives, we have only the normal direction. We don't have any tangential direction. Why? So in general, of course, we should keep the tangential direction and continue to integrate it, assuming some constant, and see what happens. But here our sole purpose is to let's say account for the pressure difference because of the discretization, and that pressure difference will happen only in the normal direction. So whatever variations we are looking for, they will appear only in the normal direction. We don't care about what happens in the tangential direction, and we drop all the terms which have derivatives in tangents. So if we do that and write down our interface tracking equation, this is the term in the red one is the term we have as the, let's say, driving force that will cause our order parameter to deviate from its some equilibrium given shape. Again, this we can, as we already said, that kappa into this interface width, we can identify some small parameter alpha, and we can again write in this way, so that all the information about the problem is now contained in the equation. So we have epsilon and we have alpha, and this drives the, let's say, the deviations. If epsilon was 0, we expect that this should really boil down to the any given equilibrium solution. In this case, it is a tan hyperbolic. It really doesn't matter. We can use any sort of interpolation function, but as long as this epsilon is 0 or the discretization error is 0, we know what is the analytical solution. So since this is our error term, right? So we already know where to look for the deviations. So we write the order parameter as some equilibrium value plus we start with epsilon square, and then we include alpha and alpha square also. So with this, this is the only part. As soon as we put this in this equation, what we are looking for is term by term solution. So we are looking for solution for phase field in epsilon square and again in alpha and alpha square. So if we substitute all these expressions and if we demand for mass conservation, so this is the condition for that. That there will be some equilibrium profile, and all the deviations from this equilibrium when integrated in the normal direction, right? So they should average out to 0. So this is the boundary condition, that far away from the interface we should have all the deviations should go to 0, and the mass conservation, because now we have a geometry that is not necessarily a flat interface, we can include also the changes, the factors to change from Cartesian coordinates to curvilinear coordinates one. So we'll have a term depending on alpha and eta. So with these two conditions, we can find out, let's say, all this deviation. Let's say phi to 0, we can, in this case, we can really find out what is that term. So the left hand side is the expression, and the right hand one is what we find from the simulations. The physics, not so, since everything is numerical, right? But still we say that there is some physical meaning. So the physical meaning for this is what we are saying is that Phi 2 0 really corresponds to a sharp interface where we don't have any alpha contribution. So here we don't have any alpha contribution. Then phi 2 1, the first index shows the epsilon dependence, the second one shows the so this is supposed to in fact take care of the flat interface, and there is some correction if our interface is slightly curved. So these simulations agree well with this type of let's say the solutions we find. Phi 2 2, however, we could not find it analytically. So one has to numerically integrate, but our agreement was poor with the simulation, so I have not included that here. But we'll come to that in the next slide. So once we find out, let's say, what are the deviations of this order parameter from equilibrium, we can simply look at again the momentum balance equation. Until now we looked at the interface tracking equation, how much was the deviation of the order parameter from its equilibrium profile. Now we are writing the momentum balance equation. Again, our driving force starts at epsilon square, so we are expecting pressure variations in the same fashion. And if we substitute all the values and take average along the interface, we would find that the numerical pressure and the analytical pressure are related by something like a formula like this, where I have not included the alpha square term, so we'll come to that in a moment. So this is the let's say the most important term. This is the term which even if we have zero curvature, this term will be there, 1.333. In the order of alpha, the integral in fact is analytically equal to 0. So there is we don't expect any effect in alpha. Alpha square, there some term appear, but again that was we could not. Our simulations and analytical let's say these predictions were not in agreement. So this is still okay. This is still okay as soon as we look at the graph. So this is, let's say, the graph. We can plot our error in pressure as a function of epsilon and alpha. What we see here is the dependence on alpha is really small, which is already clear here. Just that we are not able to show or go to the terms in alpha square, but numerical simulations already tell us that these effects are very small. And what is, let's say, the message from this final graph is this. We started with error somewhere around 6%. Let's say this was the magnitude of the force, the unphysical force, and we can reduce it to let's say somewhere around 1%. So this is for the course, the most, let's say, this is the worst possible simulation one can do. And if you are slightly careful, then the error is 0.1%. So we can again, the message is that we cannot satisfy the momentum balance exactly, which is again true for all models. But then we have a way of already working with this coarse resolution. And what we learn from this coefficient is that although our results we find, although our results we compared only with circles, they are equally true for any arbitrary deformed shape, right? So we don't have to worry about what happens if the drop was deformed and we are looking for pressure difference outside and inside. So that should still work. So yeah, so with this I will, this is a summary.
Long live India and France friendship.